And I had an enjoyable time pulling this presentation together, basically to try to summarize and put in a systematic form the work that's been going on over the last decade or so on how flames, both premixed and non-premixed, I'm also going to talk about non-premixed flames, how they respond when they're harmonically excited. So this is a different type of problem than the turbulent combustion problem, although our flames may be turbulent, because the classical turbulent combustion problem is we're trying to understand how basically broadband stochastic disturbances alter time average properties of flames, like time average burning rates. And here what we're looking at is what happens to flames, and in particular what happens to their phase lock or their time or their ensemble average dynamics when we force them with periodic disturbances. So that's my focus. And so I want to acknowledge many of the graduate students who've worked with me on these problems, and I certainly, for those of you from IIT Madras, you may recognize that more than half of these names come from IIT Madras. Santosham Chandra was now at the Indian Institute of Science in Bangalore. Shri Krishna works at GE. Vishal Akaria is a research engineer working for me. Preetham works for GE's Global Research Center. So these are all from IITM. Oh, and I just have one small advertisement for a textbook that I've been working on the last 2 years on a very related topic. It's called Unsteady Combustor Physics. It's available from Cambridge. It's a textbook, so it has exercises. It's about 530 pages. And the idea of this book was to bring together the fields of combustion, acoustics, and hydrodynamic stability into one package. And so the first section of the book is on flow disturbances in inhomogeneous environments. So hydrodynamic flow stability, acoustic wave propagation, things like that. The second section is on reacting flow dynamics. And then the third section is on transient and time stationary combustion phenomenon. And so really the focus of this particular workshop is what's really focused on in chapters 11 and 12, with looking at how flames respond to excitation. So, all right, so as I mentioned, the idea here is I want to look at is how do flames respond when they're harmonically excited. So as will be obvious to many of you, when you have a combustion instability, these manifest themselves as very narrow band oscillations. So I have here a spectrum of an instability, a spectrum of the pressure during an instability, and you see these very narrow band features. These are narrow band oscillations associated with natural acoustic modes of the system, and these narrow band oscillations lead to flow oscillations and that excite the flame. And so if you really distill it down, the basic problem, you can boil it down to a wave equation, which I have on the left side here, being excited by a source. And really one of the key issues here in understanding combustion instabilities is understanding the combustion response, understanding the sensitivity of these unsteady heat release to flow disturbances in the system. Oh, okay. So how do we relate, Q prime, where Q prime is what I'm going to call my unsteady heat release, to fluctuations in pressure and velocity and so forth. And once we can do that, then we can solve this wave equation. And so just this is a basic feedback loop where we have heat release oscillations which excite acoustics. These acoustic oscillations can both directly excite the flame, but probably more relevant is these acoustic oscillations excite inherent flow instabilities, hydrodynamic instabilities of the flow, oftentimes manifesting themselves as large-scale vortices. And then these large-scale vortices excite the heat release. So, by the way, so I always wonder, so I don't know what happens in Germany, but in the United States, students sleep in the first talk after lunch. Especially now that the lights are dim. So in fact, I slept when I was a student. So now when I teach, I always tell people that, I understand everybody has a hard day. And so I let 2 people sleep, but only 2. So the third person, I tell them that they have to coordinate among themselves and say who's going to sleep. Because then I start to take it personally if there's more than two people sleeping at any given time. So the focus of this talk that I want to get into is the sensitivity of the heat release to flow disturbances. In particular, by flow, I'm talking about velocity, mass flow rate, if I have fluctuations in the flow, how does this lead to oscillations in heat release? This is the question I want to dig into. And so, in particular, what I want to look at, let me back up for a minute, is here's an equation for what I'm going to call the global heat release of the flame. So capital Q will be global. It'll be if you take the heat release from the flame and you spatially integrate it. I'm going to call that capital Q. And since I've spatially integrated, it's only a function of time. And within the flame-lit approximation, so if my flame is a thin sheet, this heat release, I can collapse it to a surface integral over the flame, and it's the product of two quantities. This quantity right here, what I'm calling m dot sub f, is the mass burning rate. It's the rate at which the flame is turning fuel into products. All right? So if this is a premixed flame, this mass burning rate is the density times the flame speed. If this is a non-premixed flame, the mass burning rate is proportional to a diffusivity times a gradient in species concentrations. And then this H sub r, this is the heat of reaction. This is the amount of heat that's released per unit of fuel that's consumed, and then I integrate this whole thing over the flame surface area. And so when I have oscillations in flow, as I'll show you lots of movies, it moves the flame around and it wrinkles it and it causes fluctuations in flame position. Those show up through causing the flame surface area to oscillate. And also what can happen is that when I have flow fluctuations, it can cause stretch and strain, oscillatory stretch and strain on the flow for premixed flames, or it can cause time-varying gradients in species concentration in non-premixed flames, and those influence the mass burning rate of the flame. So really what I'm going to be talking about in this presentation is, first of all, when I have flow oscillations, how do these knock the flame around? What is the space-time dynamics of the flame position? And then that's going to feed into this dA. And then also what I'll talk about is how do these also influence mass burning rate oscillations? And if I put the whole thing together and integrate it, that gives me my heat release. So I'm going to talk both about the local response of flames in the first half of this talk. So when I perturb a flame, just what is the space-time dynamics of the flame sheet position? And then I'll talk about the global response, which is the spatial integral. And so there's lots of questions that we can ask ourselves, which I'm only going to barely scratch the surface, and I know a number that Dr. Pascherite later today is going to be addressing, as well as others tomorrow, is questions like, here's a plot of the unsteady heat release as a function of the magnitude of the velocity disturbances. So U prime is the fluctuating velocity, Q prime is the fluctuating heat release. And you can see that there's some regime where this plot is, and this is data, where there's an approximately linear dependence, and you might ask, well, what are the factors that affect the slope of this curve, the gain relationship? And here I have a gain, which is just basically the slope of this curve as a function of some dimensionless frequency. What are the factors that control the characteristics of this curve? And then in a nonlinear situation, in this particular case, we have a very strong saturation. Why is it saturating? What are the physical processes? Why is it saturating at this amplitude? In this case, at about 40% of the mean heat release. But you look at other data, it might saturate at 10%, down here, or some other cases it might saturate up here at 100%. So why at that amplitude? These are some of the questions that we're interested in addressing. Okay, so Professor Polifka asked me to provide some background on the basic equations that we're going to be using. So before I talk about flame dynamics, I just want to take a quick sidelight and just walk through the analytical tools and the governing equations that we're going to use to look at these dynamics. And so what I'm going to do is I'm going to work within the fast chemistry limits. So I'm going to assume that I'm working within the flame-lit approximation. So in a premixed flame, that means that the flame is a very thin sheet, and I'm just going to basically be collapsing all the complex chemistry into a discontinuity. And in the non-premixed flame, it also is a thin sheet. And so I'm going to use the G equation to describe the premixed flame and the Z equation to describe the non-premixed flame. And I'll explain to you what those are. So just very quick derivation. The Z equation is going to be my equation to understand non-premixed flame dynamics. And so the key assumptions that I'm going to be making to do this analysis is, first of all, I'm going to assume Lewis number is 1 and that the flame occurs at the Z stoke, or the stoichiometric mixture fraction surface. So Z is my mixture fraction. And I'm also going to assume equal diffusivities. And so then I basically have an equation of this form, a convection diffusion reaction equation for the fuel, which looks like this, for the products, which looks like this. I can add these, get an equation of this form. And then if I recall the definition of the mixture fraction, what I end up with this is a sourceless equation for the mixture fraction, which is, in a sense, an unsteady convection diffusion equation for the unsteady heat release. And as I'll mention later, the first studies that I'm aware of that use the Z equation to understand the dynamics of non-premixed flames responding to harmonic flow disturbances was actually the work of Professor Sujith. And then actually applied to understand systems by actually Professor Juniper, both organizers of this meeting. So that's the Z equation. So I want to understand, in essence, what I'm looking at is if I perturb the velocity field, this U, how does the flame both locally respond, how does the Z Stokes surface respond, as well as how does the heat release respond. Now I can do the same thing for a premixed flame, and there I'm going to use what's called, and these letters are made up, but I'm going to call it the G equation, just it's a for historical reasons. And in the G equation, again, I won't go through the derivation, but basically what I end up with is an equation of this form, which describes this scalar field G, and the flame is described. All the interesting stuff, all the chemistry is packed into this surface right here, which is where G is equal to 0. In the reactants, G is less than 0, and the products, G is greater than 0. But important to realize that, and I'll get into this in a minute, in a non-premixed flame, Z has a physical, it's physically meaningful everywhere. It's the mixture fraction. In the mixture fraction is the amount of mass of stuff that originated in the fuel jet normalized by the total mass. In contrast, the value of G doesn't really have a physical correspondence when you're in the reactants or the products. It only has physical correspondence at the flame where G is equal to 0. So this is an equation that describes the propagation of this scalar field G, and then what I need to do is I need to extract where G is equal to 0 to figure out where the premixed flame front is. And again, what I have is I have a convection operator on the left-hand side, which is just the flow velocity pushing around iso G surfaces. And then, as opposed to the non-premixed flame where I had a diffusion operator on the right-hand side, here I have a propagation operator. So SD, this denotes basically the flame speed. D denotes displacement speed, the speed of the front. And this mag grad G basically means that the front is propagating normal to itself. So at every instant, the front is propagating normal to the G equals 0 surface. And so one more simplification that we're going to make for the G equation, I'm only going to look at two-dimensional flames for this discussion. And the other thing that I'm going to do is here's a sketch. So this is an instantaneous position of my flame. And I'm going to assume that the flame position is a single-valued function of the coordinate y. And so then the flame position is given by this function zeta of y and t. All right? So obviously if the flame was rolled around and wrapped around, I couldn't do that if it was a multi-valued position. And so then I can define G in this way, substitute that into the G equation, and this is my model equation that describes the position zeta. I'm going to use both zeta and L in this talk. And it means the same thing. So kind of a nasty nonlinear right-hand side. This is my flame propagation, and this is the part that describes convection of the front by the flow. So we have convection of the flame getting moved by the flow on the left side, the flame propagating normal to itself on the right-hand side. So if we take these two equations, it's interesting just to compare and contrast them. On the left side, you can see we have the same convection operator. They basically look the same. And what that's telling us is that, and one of the things it tells us is that wrinkles are created on these surfaces, either on the G equals 0 surface or on iso Z surfaces, by velocity fluctuations normal to iso G or iso Z surfaces. Okay? The right-hand side, things look different. We have the diffusion equation. We have a diffusion operator. This is a linear operator, at least a quasi-linear operator. Whereas the premixed flame, very strong nonlinearity shows up here, and this describes, as I mentioned, flame propagation. Now, something which is interesting is that the right-hand side of both of these equations becomes essentially negligible In the non-premixed flame, in the Peckley number, much, much greater than 1 limit. So when characteristic velocity times a characteristic length scale divided by the diffusivity becomes very large, this term becomes pretty small. Or in the premixed flame, when the flow velocity is much, much greater than the flame speed, this also becomes negligible, at least in certain regions in space. And so what that means is in that limit, these equations are actually quite similar. And so we can expect some similarities in the space-time dynamics of the flame position in these limits, and as I'll show you from some exact solutions later on. But as I'll also show you, the fact that there are some analogies or some similarities in the local space-time flame position dynamics does not necessarily mean that the dynamics of the heat release are the same. And I'll talk about that as well, is that they're controlled by totally different features. Okay, one other point I want to make, and I mentioned this already, let me just make it one more time, is that the G equation is only physically meaningful at the flame surface, where G is equal to 0. And that allowed us to make this substitution that we did here. All right, but notice that what this substitution is doing is it's in essence arbitrarily assigning a value to G away from the flame position. You know, G is less than 0 in the reactants, it's greater than 0 in the products, but I'm arbitrarily assigning some value of G. I can't do this. I can't make this substitution into the Z equation because I would be assigning a value to Z away from the flame. And I can't arbitrarily assign a value to Z. I got to solve for the value of Z. All right? And so although the G equation is actually this nasty nonlinear equation, a very nice simplification is I can actually explicitly solve for in this 2D, two-dimensional, single-valued approximation, I can explicitly solve for the flame position. I can write an equation for the flame position, zeta. You cannot do that in the non-premixed flame case. All right? The Z equation is physically meaning everywhere. You can't make an analogous substitution. And so that really reflects a fundamental difference in the problem. And just to illustrate here, what I have is a bunch of vectors of the velocity field. This is actually a premixed flame. The premixed flame dynamics are only controlled by the velocity at the flame sheet itself. Now, certainly, from the fluid mechanics of the problem, there's feedback. You know, the velocity at the flame and in the flow itself, they talk to each other through the Navier-Stokes equation. But from the flame dynamics point of view, the flame only cares about what's happening at the flame sheet. In the non-premixed flame, the Z-Stokes surface is influenced by the velocity field everywhere. Okay, so if you change the velocity field here, it has an explicit influence on the flame sheet dynamics there, which does not happen for in the premixed flame case. Okay, so that's just kind of a quick overview of the governing equations. I just threw in one last slide, just some references for you to look at, which really walk through kind of the approach that I'm going to use, and I wanted to point them out to you. What I see is some really milestone studies, and I'm probably missing one or two here, but these are just some ones that, as I was preparing this, that jumped out at me. First of all, there's a very nice, in Markstein, in his book, Non-Steady Flame Dynamics, where he basically, for the first time, derived the G equation. Foreman-Williams made it rigorous in 1985, but Markstein was one who really presented this equation which you could use to start solving for flame sheet dynamics. And what that meant was we moved away from having to solve these reaction diffusion equations and really could focus on the sheet dynamics. Then there was a very nice paper, the first study that I'm aware of that actually used this to understand combustion instabilities themselves was by Marble and Candel. And this is 77. I believe this should be 72. Which was, as I said, I think it was the very first study that explicitly used this type of G equation approach to understand combustion instabilities. And then there was another paper by Boyer and Quinnard in 1983 where they really actually went in and dug into the flame dynamics. And then also Professor Bayot and Daniel Dirac, some of the first studies that I'm aware of to actually use the G equation to solve just to back up, so this Marble and Candel paper, it used this as part in a larger model to understand combustion instabilities. But one of the first studies that I'm aware of that actually explicitly focused on the flame dynamics and trying to use the G equation to predict the flame dynamics were these two. And then this study by Fleifel et al. As part of the group at MIT to actually use these ideas to actually predict flame transfer functions, which are going to be an extensive discussion of topic at this workshop. And then in non-premixed flames, first of all, the work of Peters to rigorously develop this Z-equation framework within the flamelet approximation, and then Sujith and Chakravarthi at IIT Madras to actually use it to understand how flames respond to harmonic flow disturbances. Okay, so with that as a background, so now I want to, really the rest of my talk is organized into three parts. I want to talk about premixed flame, their local dynamics, then I want to talk about non-premixed flame, local dynamics, and then I'll talk about global heat release dynamics. So first we're going to talk about just space-time dynamics. And so in other words, this is a much more complicated situation than I'm going to talk about. This is some OH PLIF images of a swirl flame. But if you think that that instantaneously the flame is this interface, what are the factors that control the space-time fluctuations of the flame as we evolve in time? That's what I want to talk about. So just to build up a little intuition, I just want to show some movies. These are some me-scattering images of a bluff body stabilized flame with different amplitudes of excitation. And you can see, what we're doing is we're actually forcing this flame. The flow is going up and down, like the flow is actually being forced, and you can see these wrinkles moving downstream. If we go to a higher amplitude of excitation, it's very clear here to see the coupling of the flame with hydrodynamic flow instabilities. You're really strongly exciting the Kelvin-Helmholtz instability of the shear layer, which is strong enough to actually start whipping the whole flame around and rolling it up. And you can see, as you watch this, you can see the action of kinematic restoration, which is the propagation of the flame normal to itself and smoothing itself out as you move downstream. So these are just some typical images of what harmonically excited flames look like. And as I said, they can look a whole lot more complicated. This is in a swirl flame where you have an OH PLIF image. You can see, this is, I really like this one right here. You see the large-scale roll-up of the flame. You can see the Kelvin-Helmholtz instability of the outer shear layer right there, the Kelvin-Helmholtz instability of the inner shear layer right there. This is a lot more complicated, though, than I'm going to get into, these swirl flames. Okay, and so here what I have is a bunch of different images. These are actually at a whole bunch of different flow velocities, ranging from 18 to 170 meters per second, axially excited. And what we're going to start doing now is I'm going to start looking particularly at the flame edge itself. So I've drawn in a line here which denotes the flame edge. And if I were to extract a whole bunch of those flame edges and overlay them, they would look something like this. And at the very high velocities, that overlay sort of looks like what you might expect from a high turbulence intensity flame, which is, this is basically the flame brush, the turbulent flame brush upon which is superposed the harmonic wrinkles. You can see this turbulent flame brush growing as you move downstream. This is what you would expect if you just were exciting a flame with turbulence. As the flame brush grows monotonically as you move downstream. This is a little bit more interesting. You don't have as much turbulence here at 18 meters per second. You can see a little bit more complicated. You can see there's this growth region, then actually the magnitude of the flame brush is actually getting narrower as we move downstream. So that's kind of an interesting result, and we're going to explain what's happening there as well. But these are some images just to give you a feel for, again, what's happening. So now let's start quantifying this. So now I've turned my flow sideways. Flow is going left to right. And I want to quantify the instantaneous edge of the flame by this variable L. I called it zeta before. Like I said, I'm going to go back and forth. L is a function of x and t. And at a given x, L is oscillating. So this is L plotted as a function of time. You can see it oscillating in time. If you take a spectrum, you can see a very sharp peak. In this case, I was exciting the flame at 300 hertz. And what we can do then is we can start looking at how these spectra evolve as you go downstream. So now I've added a dimension to that plot. So we have L prime frequency. That's what I just showed you. Now I'm going to add another dimension, which is x, axial distance. And it looks something like this. So what this is telling me is this envelope, which I can drop right there, is the magnitude of the fluctuations as a function of space and time. And so notice the non-monotonic spatial dependence of this magnitude. You can see it goes up. In this case, it comes down. Very strong response at the forcing frequency. And this actually is kind of reminiscent of that overlay that I showed you in a minute, where the flame brush it's attached at the flame base. It's not really moving much. The magnitude of wrinkling is going up, and then it's coming back down in this result. And so here I have, this is actually another result. Now I'm collapsing dimensions again. I'm only going to show you the magnitude of flame wrinkling at the forcing frequency. And so here's L prime as a function of downstream distance, and you can see it going up and coming down. Here I'm showing you the phase as a function of downstream distance. You can see a very linear phase dependence, which is telling me, well, actually I'll get into that in a minute. So you can see there's very low amplitude fluctuations near the attachment point. It grows as we move downstream. There's some peak. The magnitude of flame wrinkling is peaking at some location, and it's decaying as we move downstream. And then if we look at the phase, it's approximately linear in distance, which is telling me, when you see this linear dependence, what that means is that the wrinkle on the flame is moving at a nearly constant velocity with downstream distance. The slope of this curve is directly proportional to the speed with which those wrinkles, when you could see in those movies, you could see the wrinkles moving downstream. The velocity of those wrinkles you can directly extract from the slope of that curve. Now, this is kind of a simple one. This is kind of an easy one. But these gain curves can look a lot more complicated. And just to illustrate, these are two other gain curves from some other conditions. Again, L prime is a function of downstream distance. Notice that you see the same general envelope. It starts near 0, goes up and comes down. But now you also see this this shorter wavelength modulation of flame wrinkling. All right, so that's an interesting one. And you can really see it in this one. This almost looks like a standing wave. So you can see the flame wrinkling. That flame is really not flapping around much at all here. It's flapping around quite violently there, or there, or there. But it's, there's kind of this node, antinode type response. But this isn't acoustic waves. This is the flame position. Okay, so I want to understand this. And there's really 4 things going on here. So I'm going to walk through these 4 things. And the first one is wrinkle convection. So in order to understand wrinkle convection, it's easiest to look at the impulse response of the flame. So for those of you who had combustion, if you think about it, we all know that if you take a flame, a premixed flame, in a flow with a velocity of UA, so let's just assume that I have spatially uniform bulk velocity given by UA. And you know that the flame settles at some angle, so sine theta will equal SL over U. Right? That's kind of an equation for the flame position. But I want to look at its impulse response. So at time 0, I'm going to make a step change of the velocity from a value of UA to UB. And so what that's going to do is it's going to change the flame angle. Right? The flame is going to be at one angle. If I increase the flow velocity, it's going to change to a new angle. But the question is, what's the transient look like? How does it respond? Does it swing out, or does it, what does it do? And what happens is, this is a little movie that shows you that transient response. And so what you can see is you basically get this, let me just go to the next slide. You get this discontinuity in slope that moves downstream. And on one side of that discontinuity, the flame has that angle sine theta equals SL over UB. On the downstream side, the angle of the flame is sine theta equals SL over UA. All right? And the transient response of the flames is basically this wave that moves downstream at some velocity, which is not the flow speed, by the way. I'll talk about it in a little bit. But you get this wave that moves downstream and that's how the flame adjusts itself to oscillation, to this step change in flow velocity. So, and in fact, you can see this. One of the easiest ways to see this is actually it's a really nice visualization taken in 1961 where Peterson and Emmons just took a bluff body and they just shook it sideways. All right? And by shaking it sideways, they changed where the flame was in space, and you can clearly see these harmonic wrinkles moving downstream. And the speed with which the wrinkles move downstream, I'm going to call that speed UT. All right? In order to understand why this speed UT is different than the flow velocity, we can look at this construction. Here's the flow is moving downstream at a speed of u naught. So the flow is pushing the flame downstream at a speed of u naught. But the flame is propagating normal to itself at a speed of SL. And so if we just do the vector addition of u naught plus SL, we get UT. And UT is the speed with which wrinkles are moving along the front. So it's a function of both the flow velocity and flame propagation which control this wrinkle this relaxation process. And so just an important point here then is that here, just to illustrate this, what I have is a graph of normalized convection velocity. So I have some velocity, which I'll talk about in a minute, normalized by the flow velocity as a function of downstream distance. So if it has a value of 1, this thing's moving at the mean flow velocity. And these lines right here, this line right here, this is the convection speed of the flame wrinkle. I'm calling it UCF, the convection speed of the wrinkle on the front. And notice it's not U0. It's a little less than, it's a little greater than right there, but it's not U0. And just for fun, I've also overlaid, we had PIV data. This plot right here is the convection speed of the vortex, which was exciting the flame. And notice how the convection speed of the wrinkle is not the same as the flow velocity, which is not the same as the excitation source, the vortex exciting the flame. So you have these 3 characteristic velocities floating around in the premixed flame problem. And as I'll show you, a lot of the really interesting interference processes that are occurring on flames are because these things aren't moving at the same speed. Okay, so let's go back to that harmonically oscillating bluff body, that Peterson and Emmons plot. And if you just sit down and you solve that with the G equation, I'm not going to, but if you do it, and if you linearize the equation, so you turn off the nonlinearities, so you assume very, very small amplitude wrinkles, and you assume that the burning velocity is a constant, so that the flame speed is fixed, it doesn't vary in time, then what happens is when you harmonically oscillate that bluff body position, what you're doing is you're exciting the flame position at x equals 0, and then this plot just shows you the magnitude of the flame wrinkling as a function of downstream distance. And it's kind of boring. It's constant. So what that tells you is the flame basically looks like a traveling wave, the response. So if I have this harmonically oscillating bluff body, I excite a wrinkle, and that wrinkle just moves downstream at the speed that I called UT or UCF. But the magnitude of the flame wrinkle does not change as I move downstream. All right? This looks quite different, obviously, than the data that I showed you earlier, so there's more that we're going to need to account for. The phase looks something like this. So you get this linear phase roll-off, which actually doesn't look too different from some of the data. And this linear phase versus downstream distance, this is that wrinkle convection process, which I'm emphasizing here. And as I'll talk to you later on if I have time, if you want to understand why flames act as low-pass, why the heat release acts as a low-pass filter, it's all driven by this curve right here. Okay. All right, so I've talked about wrinkle convection. Now let me talk about, so I've talked about what happens once you create a wrinkle, what happens to it in the linear approximation as the wrinkle just moves downstream along the flame. Now I want to talk about how do you excite these wrinkles on the flame front. All right, and in order to do this, I want to go back to the equation for the flame position, and here I've written it in terms of, instead of zeta prime, it's L prime, but again, it's the same thing. And rather than solving for the flame position itself, it's a little bit more convenient to look at the slope of the flame position. So here I'm looking at dl prime by dx. So it's basically, this is an equation for the fluctuations in slope of the flame position. And if you solve that equation, you get this thing, all right? It's a convolution integral here. And this is the particular solution. And this is a term which is a function of the fluctuating velocity x equals 0. This is the homogeneous solution. And I'm going to talk about these in a minute. So when I've done this is a linearized solution of the G equation. I've assumed it, and I've also assumed an anchored flame. I've assumed that the flame position right there does not move. As the flow is moving back and forth, the flame stays fixed. It stays attached. First of all, you can clearly see wrinkle convection. Notice these delay terms. You know, this is t minus x prime over ut, t minus x over ut. This is that wrinkle convection showing right up there. And I talked about that before. What you can also see is that the velocity, which is a vector, only shows up in scalar form in the G equation. All that matters is what I'm calling un prime here. Un prime is the fluctuating velocity normal to the front. So the flame doesn't care about the vector velocity field. It cares about the scalar component of the velocity normal to itself at that position. So I want to break this down into two pieces. So first I want to assume that I have a bulk disturbance field. So a disturbance field that does not vary spatially. The disturbance field only varies in time. All right, so just the whole flow is sloshing up and down. So this might be an approximation for a flow where I could somehow suppress the excitation of hydrodynamic flow instabilities, I just have a really long wavelength acoustic disturbance, just knocking the flame back and forth. So in that case, this whole term goes away, and I'm left with just this term right here. All right, so what's interesting about this is that the remaining term is only a function of the fluctuating velocity at the attachment point, at x equals 0. So you get this wave, it's generated at the attachment point, and it convects downstream. And can you guys see that in the back, the flame edge, if I play this movie? So, and here's a movie, just a zoom of a, I can't see it, is it moving? Okay. And so what's happening here is that this fluctuating velocity, so if you look there, you'll see the oscillatory flame angle at the attachment point. This is a circle of pilot flames to hold this flame on. You see the flame oscillating, and then that, if you kind of can watch this put your Lagrangian point of view eyes on, and you just watch that wrinkle, it'll just propagate downstream. You can watch it with essentially fixed slope. So that's that term right there. And so one thing that's interesting about this is it shows you that if the excitation velocity is spatially uniform, the flame response is exclusively controlled by what's happening at the attachment point, at x equals 0. All right? This what I'm calling the flame anchoring boundary condition. So here I assume something simple. I said the flame's attached, it's fixed, it's not moving. But if the flame was moving, that motion at the attachment point, that's what's controlling the entire problem, what's happening at every other point in space and every other point in time. And so kinetic effects, diffusive effects, heat loss effects, all the stuff that controls flame anchoring and flame stabilization, although I haven't explicitly talked about it, that's going to control that. You basically have an edge flame right there. All those edge flame dynamics, they're very important, and this is where it would show up, is that these anchoring boundary conditions are important. They really, really matter. Did I do that? So this is a good time to take a break. Okay, so I was talking about how, can I start? I was talking about how flame wrinkles are excited, and I had started with the simplest case for a premixed flame, which is just a bulk disturbance, a disturbance with no spatial variation, just the whole flow field sloshing up and down. And the main point I wanted to emphasize there was that in that case, the problem is totally controlled by your boundary condition, or what's happening at the flame attachment point. I solved this problem assuming that the flame stayed fixed, but if the flame didn't stay fixed, whatever's happening there completely controls the problem. Okay, so now let's I'm starting to talk too slow, so I'm just going to jump over some stuff. The other point I want to just real quickly make is that because the flame is starting out with basically very negligible wrinkling, what I'm going to call the near field dynamics, what's happening to the flame space-time dynamics near the flame attachment point is basically linear in amplitude. So there's going to be lots of discussions around nonlinearity and things like that. The flame nonlinearity accumulates with downstream distance. It's actually very much like acoustics with shock waves, where nonlinear effects accumulate as you propagate downstream. Same way, flame propagation, which is the key nonlinearity for premixed flames, those effects accumulate with downstream distance. And so nonlinearity is not uniformly felt over the flame. The near field dynamics are very, very linear. And just to show you this is a plot of the magnitude of the flame wrinkling L prime as a function of downstream distance. So you've seen this plot, this red one before. But here now what I've done is I've overlaid 3 different amplitudes. All right? And you can see they're all starting near 0 and they're all rising. But if you take this same data and you normalize it by U prime, notice how all the results collapse in the near field. So near the flame holder, the flame is pretty linear. Even at high amplitudes, the region of linearity collapses to a region that's closer and closer to the flame holder as you move up in amplitude, but it stays linear near the attachment point. Okay, so I've talked about excitation of wrinkles. Now I want to talk about interference processes. And so I want to go back to this equation that I showed you before. And before I had X'd that term out because I said, let's look at spatially uniform disturbances. So now let's think about what happens when the velocity fluctuations, d by dx, is non-zero. And so what this equation tells us is that flame wrinkles are generated at all points where the disturbance velocity is non-uniform. And what this is a convolution integral. So what this also shows you is that the flame wrinkling at a point, if this is my flame attachment point here, and this is a flame propagating, if I want to understand why the flame is the wrinkling here, it's not just the velocity fluctuation here that's controlling the flame wrinkling. It's a convolution of all the disturbances at every upstream point with a suitable time delay. Right? So the entire space-time history of the velocity field at all upstream points controls the flame wrinkling at a given position downstream. That's what this convolution integral is telling you. So what I specifically want to look at this is in the case where the velocity field consists of a convecting vortex, which is a very, very interesting problem for a combustion instability point of view. So the vortex is convecting at some speed of uCv, and as we've talked about, there's really two. I mentioned 3 velocity scales, but I'm going to focus on 2 here. There's the speed with which this velocity disturbance is moving downstream, which I'm going to call uCv. And then there's the speed with which this flame wrinkle that's excited is moving downstream. And here I've called it ut. And again, they're not the same. I showed you this graph earlier, which just shows you that the speed with which the vortex is moving and the speed with which the flame is relaxing to that vortex, they're not the same. So this starts to suggest interference effects, right? In many electromagnetic or acoustic problems, we get interference effects, we get standing waves because we have disturbances moving in opposite directions relative to each other, and we set up standing waves. But you can also get interference effects by having 2 disturbances moving in the same direction but at different velocities, and they'll move in and out of phase with each other spatially. They're not standing waves because there's a spatial, they don't stand like acoustic waves do, but you can clearly get node and antinode behavior. And that's exactly what happens with premixed flames. Is you get these 2 disturbances, you get the flame relaxing, this wrinkle convection effect. So you excite a wrinkle and it moves downstream, but it's continuously being excited by something moving at another speed. The speed with which the vortex is moving is non-trivial. You know, if you look at there's lots of measurements in the combustion instability literature, and you'll see lots of numbers out there for the speed with which the vortex is moving. And this just goes back to the fact that hydrodynamics instabilities are dispersive. You know, the speed with which they move is strongly sensitive to frequency, to shear layer thicknesses, and things like that. Just to illustrate that, this is a JFM paper. It was actually one of the first papers to measure these very high velocity convection speeds of these Kelvin-Helmholtz instability waves. And this just shows you the convection speed of the vortex as a function of a shear layer Struhal number for different boundary layer thicknesses. So just to illustrate this point, let's look at a very simple model problem. All right. So I looked at a bulk velocity disturbance. Now let's assume that the unsteady velocity that's disturbing the flame has this space-time disturbance type feature. All right. So t minus x on uCv. So this is basically a velocity disturbance with fixed amplitude moving downstream at a speed of uCv. Okay. You can derive the solution for it. And basically, there's 2 terms. There's 2. This is in complex notation. You see a uCv here. You see a u. This is that ut. This is the term reflecting the excitation of the wrinkle by the vortex. This term here is the natural relaxation of the flame. And you can see there's these 2 complex exponentials subtracting each other. And if you actually plot the magnitude of the flame wrinkling excited by that disturbance, this is what you get. So this is the magnitude of the flame wrinkling as a function of downstream distance. And notice this behavior. You get this basically node, antinode type behavior. You get this interference pattern. And what you also get is a new length scale. All right? This interference length scale. And this interference length scale is directly related to the difference between these 2 velocities. The speed with which the wrinkles are propagating along the front, the speed with which the vortex is moving that's exciting the flame. If those 2 are equal, this wavelength becomes infinite. There's no interference. As soon as those 2 wavelengths are as soon as those 2 convection speeds are different, you set up this interference pattern. All right? And if you go back to some of the data that I showed you earlier, this is exactly what we see when we look at data. Here's a very, very strong interference pattern. Here, there's actually 2 length scale interference patterns. There's a long length scale. This is the vortex. You can also see the short wavelength modulation. This is actually the acoustic wave. I really like this graph here because it shows, in general, when you have an instability, you have both acoustic waves, which are moving with a very fast phase speed, exciting the flame, and you have vortical disturbances, which are moving near the flow speed. And remember that the more that the phase speed of the disturbance differs from the natural propagation speed of the wrinkle. The more they differ, the shorter the wavelength is. So the acoustic disturbance, which has a very long wavelength, actually excites this much shorter wavelength wrinkle on the flame than the longer wavelength disturbance excited by the vortex, because its speed is much closer to that of the natural wrinkle convection. So, but this, I like this plot because it really shows you that the flame is being disturbed by both vortical disturbances and acoustic disturbances at the same time, and this is how the flame filters those out because of the differing propagation speeds. Okay. Now, I want to make one more point here, and I want to emphasize that this interference effect is totally controlled by the fact that we have disturbances which are coherent in space and time. If you sat down and solved a problem where you had a convecting disturbance, so but with a random amplitude, all right? So you just, to simulate turbulence, you just said, let me just take turbulence, let me convect it through. This is the result that you would get, all right? For magnet, in fact, here it's RMS value of the flame wrinkling amplitude. And so this starts to look like turbulent flame brush growth. We know that turbulent flame brushes, they grow monotonically as you move downstream. And that's what's happening here when you have a random excitation. But when you have single frequency excitation, you get this interference type behavior. And when you have a turbulent flame, which is excited harmonically, you're going to get the superposition of that with that. And if you think back to some of those images I showed you earlier, you could exactly see that. Okay, so last thing I want to talk about with premixed flames is destruction of wrinkles. Why do flame wrinkles go away? All right. Well, flame wrinkles go away because of the fact that premixed flames propagate normal to themselves, what's called Huygens propagation, and that is an intrinsically smoothing effect. So here's an image of if you take a flame which has this ripple on it and you say, okay, let me just see what happens. Let me let this flame propagate normal to itself. You get this destruction of flame surface area, and so this flame, given enough time, will look something like this. And you can really nicely see, this is a movie made by Daniel Durox, and I think this is the one that's not, so I'm going to have to pull this video up.
Sorry, just 1 second. Stop. Okay.
Sorry, all the movies are working except for this one. So I really like this video from Daniel and the group at Ecole Centrale, because you can really nicely see this kinematic restoration. So you see this is a Schlieren image of a Bunsen flame, so you can really nicely see the almost spatially periodic disturbance. But then as you move this thing downstream, you can see this cusp appear, and you can see this destruction of flame surface area as you move downstream. And so the flame becomes non-symmetric. The concave part and the convex part start to act very, very differently because one is propagating into itself. I can go back to it now. And the other is propagating out. And so you get a change in length scales as well, is that you start out with a disturbance with one length scale and you start creating longer and shorter length scale disturbances. And the shortest length scale disturbance basically collapses down to the flame thickness because you get this cusp formation where in you basically get this discontinuity in derivative. Okay. So the way this typically manifests itself in thermoacoustic instability problems is you get vortex roll-up. So if you just take a passive scalar interface, and you just take a passive scalar, it might roll up it might look something like that. Or even a flame with a low propagation speed. But then you say, okay, well, let me let this flame if this is reactance, let this flame propagate normal to itself. And given at some later time, it won't look like this, it'll look like that. Okay, and that's kinematic restoration. So I showed you this movie earlier, and you can very clearly see that kinematic restoration. Really strong vortex whips that flame around at the base. As you move downstream, it gets smoothed out. But this is a nonlinear effect. If you want to understand this effect, you have to turn on the nonlinearities. You can't just understand this from a linearized level set equation. So process is very amplitude dependent, very strongly nonlinear. So this just shows you, in order to dig into this a little bit, if we go back to that oscillating flame holder problem, here we turned on the nonlinearities. You can see the wrinkles being excited, and here's reactance, and you can clearly see, notice how the magnitude of the wrinkles is decaying as you move downstream. And this is that kinematic restoration effect. You can see the cusp formation, but also the the height of the wrinkles is decaying. And so what this does is this process accumulates as you move downstream. And so this leads to nonlinear effects becoming very important. At some point downstream, nonlinear effects are going to become important. Depends on your frequency, depends on your velocity, depends on your amplitude, but nonlinearities will be important. This is a result I showed you earlier where I showed you the magnitude of the flame wrinkling normalized by the velocity, and I showed you how all the results collapsed in the near field, but they're not collapsing in the far field, clearly showing you that they're nonlinear. And in order to demonstrate the amplitude dependence of the decay rate, I want to show you some solutions now. This is a plot of L prime as a function of downstream distance when I'm exciting a flame with 3 different disturbance amplitudes. And here I've shut the nonlinearities off. This is the scaled linearized solution. And I've also chosen a result where the convection speed of the vortex is the same as the disturbance field, so I get no interference effects. Okay? So as I turn up the amplitude of excitation, the magnitude of flame wrinkling goes up monotonically when I just solve the linear equation. Now if I turn on the nonlinearities, I get something that looks like this. So notice how the magnitude of flame wrinkling is dropping. Okay, so that's this decay effect. If I turn up the amplitude a little more, notice how the departure of the linear and nonlinear solution occurs earlier and how this decay happens quicker. If I turn it up even more, notice how it happens even quicker. What's also interesting is notice how all these results converge to a common curve. So I'm talking too slow and I can't explain to you why this is, but this is something that you would theoretically expect, is that, all these results converge. In the near field or in the midfield region, you get these different curves at different amplitudes. Far enough downstream, the results are all going to converge. You can actually see this in the data as well. If you turn off the normalization, notice how all these results, different amplitudes, how they're all converging. And so this just explains why, and I'm not going to get into it. Okay, so I just want to very quickly glance over 2 topics. So I've talked about why laminar flames with constant burning velocities, why wrinkles go away. It's from kinematic restoration. There's 2 other effects which also happen in real flames which also make wrinkles go away. And one is if you have turbulence on top of these harmonic flow disturbances, you get all these small scale wrinkles which are also chomping away at your flame wrinkles. And this is just a visualization of that same oscillating flame holder problem, but with background turbulent effects, and these turbulent fluctuations also smooth out flame wrinkles. So when you have, in any real turbulent combustor where you have both harmonic and stochastic disturbances, there's some really interesting nonlinear interactions between those 2 things. So that's all I'm going to say about that. The other effect that's interesting is that if you start thinking about non-constant burning velocity effects, the flame speed can start to modulate in time when the length scale of wrinkling gets short enough, because then flame stretch becomes important. Flames are sensitive to curvature, flames are sensitive to spatial inhomogeneities in flow velocity, and then you get flame stretch effects going on. And you can see this is a Bunsen flame. You can see very short length scale disturbances, and notice how those wrinkles just go away as you move downstream. That's a flame stretch effect. So stretch effects, and you can understand this destruction of flame wrinkle processes from purely linear arguments. This is a linear effect that makes flame wrinkles go away. For constant burning velocity flames, you have to keep the nonlinearities. If you have a thermodiffusively stable flame, linear effects also. But it's a high frequency effect. You've got to go to higher frequencies. Okay. So, all right, so that's premixed flames. Now I want to move to non-premixed flame sheet dynamics. All right, and I want to start comparing and contrasting things. I'm going to go a little bit quicker here. Here what I'm going to do to illustrate this, I'm going to pick up a model problem from Sujith where we have fuel and oxidizer, a 2-dimensional flame, and I'm going to look at a flow where there's bulk forcing. So the flow is oscillating side to side like that. And I'm going to show you some illustrative solutions in the Peckley number much, much greater than 1 limit. So in other words, where this width of the burner multiplied by the flow velocity divided by the is much, much greater than the diffusivity. And this is an interesting physical limit. Okay, so if you solve for the z field, all right, so remember here now I can't explicitly solve for the flame position because of those differences I talked about. I just jumped right over it. I could for the premixed flame. So this is a solution for the entire, so notice I have y, this is a 2-dimensional problem, so I have both x, y, and t. They're all here. So this is the entire z field, all right? This is what the series solution looks like for the fluctuating mixture fraction. That's z1. And this is a movie. So, and this just shows you a visualization. This is what that fluctuating Z field looks like. Can you see the moving around? Okay, so that's what it looks like, and you can see these wrinkles, and you can see if you watch them, you can actually see them moving downstream. What I'm really interested, though, is the location where Z is equal to Z stoke, because that's the flame sheet. All right? And there it is. There's Z stoke. So that's where the reaction is going to collapse in this flamelet limit. All the action is going to be happening right there in terms of reactions. So what I'm really interested in is what are the dynamics of this front. And that's a harder problem. So what I'm going to do here is this dashed line is the time averaged Z stoke field. And I'm going to define this variable zeta1 in, which is the instantaneous fluctuation of the flame position normal to that. All right? So with a little bit of math, what I can do is I can take this solution and I can extract, if I linearize this solution, I can extract the flame position. All right? So I have to do it after the fact. Notice that for the premix flame, I can write an equation explicitly for this. Now I have to extract it from the solution for the full Z field. And here's what it looks like. All right? Here's zeta1 in. So this is the fluctuation of the flame position. And so you can see it goes as 1 on F. There's this low-pass filter characteristic. It's multiplied by sine theta naught of x. Theta naught is the instantaneous angle of the mean flame. And so what this is basically telling you is that the local flame wrinkle only occurs through velocity fluctuations normal to the flame. Here is a convection operator in complex form. And this is telling you that flame wrinkles propagate with the axial flow. Notice that the speed of propagation of these wrinkles is the axial flow velocity. All right? So in an illustrative result here, what I'll show you, I can't remember if this is a movie or not. Oh, okay. So here's an illustrative result where the convective wavelength is 3.3. So one other thing about this is that, so there it is. So in this case, the convective wavelength of the disturbance is 3 times longer than the flame length. Okay? So this is a long wavelength disturbance. This is what the fluctuation in flame position looks like, zeta1 in as a function of downstream distance. Notice there's a node, which is occurring right there, and you get this type of behavior. So this is interesting because premix flames, long wavelength disturbances, you don't get this node on rather the flame wrinkle would just start near 0 and it would just monotonically rise. So fundamental difference here, non-premix flames, even in the limit of really, really long disturbances, you still get this node behavior, which happens right there where the flame turns over. And here's the phase. Phase, basically linear phase roll, 180-degree phase jump at that node, linear phase roll. Okay, here is a higher frequency disturbance. Here's where the convective wavelength is half of the flame length. And there you go. Now you can see it's a lot more complicated behavior. And we really and this shows you the gain curve. Okay, so now we have 2 nodes, and notice how there's this complicated space-time. This complex spatial modulation and amplitude. There's 3 local minima, 2 nodes in the wrinkling. And then the phase, linear, 180-degree phase jump, linear, so forth. Okay, so let's just compare and contrast if I take a premixed flame responding to bulk flow disturbances. So this is a bulk disturbance, so no spatial variation of the flow field. This is that premixed flame solution. I didn't explicitly show it to you before, but here's what it looks like. Here's the non-premix. And they look pretty similar. I've laid them out so that they look similar. Notice that they both have the exact same amplitude 1 on F feature. They both have this sine theta. The premix flame theta is a constant, whereas the non-premix flame, the angle is changing with downstream distance. You get a very similar looking convection operator. The only difference being is that the convection wave speeds are different. Is that in a non-premix flame, this wrinkle is moving with the flow speed. In a premix flame, it's moving with this vector superposition of the flow velocity and the flame speed, which gives you this UT naught. Okay, so that's all I'm going to say about local dynamics of non-premix flames. So I've talked about why these flames wrinkle, what controls it for premix flames, for non-premix flames. Now let's look at the global heat release What is the spatially integrated unsteady heat release? All right. So this equation right here, I want to integrate over all these fluctuations, and I want to think about what's happening. And in particular, there's two things I want to look at. First of all, there's the flame surface area. Fluctuations in flame surface area are going to cause heat release to oscillate. This term right here was the mass burning rate. Remember, this is the rate at which the flame is turning reactants into products or fuel into products. I'm going to assume, for these purposes, I'm going to assume that we have constant composition. So we don't have any fuel-air ratio fluctuations, or that the mixture fraction in the non-premixed flame problem is constant. Okay, and I'm going to work within this flame describing function formulation where I'm going to take the unsteady heat release at the forcing frequency, normalized by the velocity at the forcing frequency, and I want to start looking at this describing function. And I'm going to decompose it into two parts, what I'm going to call the weighted area and the mass burning rate. So the weighted area is basically due to the fluctuations in flame surface area. Mass burning rate will be due to fluctuations in mass burning rate. So if we start with premixed flames, here it is. Now the mass burning rate, I can write it as the density of the unburned reactants multiplied by the consumption speed, the laminar consumption speed of the unburned reactant. So that's the mass burning rate for a premixed flame. So now, if I have a constant flame speed, so SC is not varying, which it will if I don't have stretch effects and if the composition is constant, what this thing collapses to is an integral of the flame surface area. The unsteady heat release of a constant burning velocity premixed flame is just purely a surface area problem. You want to understand how the heat release oscillates, you need to understand how the flame area oscillates. Okay, let me just skip over this. And so if we take a look at the what the transfer function looks like, so if we take those expressions for flame position we've talked about before, that you now understand what's going on, and you calculate the flame surface area, and you calculate this transfer function, this is a very typical result of what a premixed flame looks like when you hit it with bulk flow excitation. All right? So the y-axis is the magnitude. So this says if I have a 1% fluctuation in velocity, what is going to be the fluctuation in heat release? Well, if the transfer function is 1, it means 1. It means 1%. A 1% fluctuation in velocity gives me a 1% fluctuation in heat release. A transfer function of 0.2 means a 1% fluctuation in velocity gives me a 0.2% fluctuation in heat release. And so you can see that this curve starts at 1, and it's very nicely explained why in this paper from Wolfgang, these low-frequency transfer functions, why they start near 1. And you can see it rolls off, and here I have it in linear, here it's in log. And so for small Struhal numbers, this transfer function is 1. For large Struhal numbers, this transfer function goes as 1 on F or 1 on ST. Okay, so first question, why the 1 on ST roll off? Why do premixed flames roll off as 1 on ST? Well, you might say, well, you already told us that premixed flames have this low-pass filter characteristic. Here was a formula that I put up earlier showing the fluctuating flame position. There's this 1 on F. However, this is the flame position. The flame area per unit axial distance, since you're going to differentiate this thing with respect to x, you're going to get another F out, and that 1 on F goes away. So the flame area per unit distance downstream does not have a low-pass filter characteristic. So it's a little bit more complicated than that. So first point, premixed flames do not roll off as 1 on F because the flame position rolls off in 1 on F, because the flame area is flat in frequency space unless you start including stretch effects. Rather, what happens is there's another effect. And to illustrate this, consider if you have a traveling wave disturbance. So take cosine of omega t minus x on u, integrate that over the flame length from 0 to LF. All right? If you integrate that thing, you get a 1 on frequency. All right? So this 1 on ST or this 1 on F in the global heat release, it comes from the spatial integration. It comes from interference. All right? And this goes back to the point that I made about why this tangential convection of wrinkles on premixed flames is so crucial, is that is what controls its high frequency characteristics. Is that when you take the unsteady heat release, what's happening here and here and here and here and here for a premixed flame, that there's a phase delay, so when you add them up, you get a 1 on omega, or a 1 on frequency effect. Okay, one other thing that's interesting to look at is the phase, and here's what the phase looks like for that bulk disturbance problem. So phase normalized by pi as a function of Struhal number, and there's this linear characteristic in Struhal number as well. And whenever you get a linear phase versus frequency effect, this is telling you that you have a time delayed problem. And you can actually show, you get this time delayed behavior with 180-degree phase jumps. And what you can do is you can show that for low Struhal numbers, you can very rigorously derive what's oftentimes called an in-tau formula for the flame heat release. So the fluctuating flame area is proportional to the unsteady velocity multiplied by some gain in some time delay tau. So this was first introduced phenomenologically by Krockow and Chang, but it actually has very rigorous application for premixed flames in the low Struhal number limit, where the flame looks convectively compact. This value of in and this value of tau, you can derive expressions for them, which I won't get into. Okay, so that's premixed flames. I'm almost done here. Now let's talk about non-premixed flames, and now let's start comparing the two. So if I take a non-premixed flame and I look at bulk flow excitation, here's my expression for the global unsteady heat release. So let me take this thing and let me linearize it. And just to illustrate this, what I've done is I've chopped this thing up into three terms. There's the steady state contribution, the time average burning rate times the time average area. Then there's a term here, which is basically the fluctuation, the area fluctuation contribution. And so it's the integral over the flame of the time averaged burning rate per unit area times the fluctuating flame area. And then you get another term, which is the mass burning rate contribution. So this is the fluctuation in the rate at which the flame is locally converting reactants to products as well. Now, for the premixed flame, remember, we only had this term right here for the premixed flame. This term wasn't present unless you have stretch effects or unless you have fuel-air ratio oscillations. In a non-premixed flame, you cannot ignore this term, and that's what I'm going to show you. So let's first start by looking at area. And so this is really interesting to start comparing and contrasting premixed and non-premixed flames. So the transfer, what I call the transfer function of the weighted area, so it's not area, it's a weighted area, and let me explain why, is if you're integrating over the fluctuating flame surface area, the fluctuating area at each axial point is weighted by the time averaged mass burning rate in that position. Now if you think about a non-premixed flame, the time average burning rate is a function of downstream distance varies strongly with position. All right? Most of the mass burning rate in a non-premixed flame occurs right near the exit of the fuel port because that's where the gradients are highest, right? The mass burning rate of non-premixed flames is proportional to gradients. Gradients are strongest right near the fuel outlet. And so notice how this curve is not flat. A premixed flame with constant burning velocity, this curve is flat. The mass burning rate is the same at every point along the flame. And so the weighted area and the area are the same thing. In a non-premixed flame, you have to think about weighted area. Area fluctuations for a non-premixed flame are irrelevant. You don't care about what the area is doing in a non-premixed flame for heat release. You care about what the weighted area is doing. And it's because of these strong variations in mass burning rate that you see in non-premixed flames with position. So let's talk about what the implications of this are. If this is a typical plot of flame position as a function of downstream distance for U on U ref of 1, okay? If I were to increase the flow velocity by a factor of 50%, the flame would look like this, okay? But what do I care about? What I really care about is what's happening to the flame right near the flame base, because this is where most of the mass consumption is occurring. So I got all this interesting stuff going on down here, don't really care about it. What I care about is what's happening here. So as you increase flow velocity, the area increases for a non-premixed flame, right? You go from the black to the red curve. However, the weighted area decreases. In other words, what I just told you is I don't care about what's happening downstream, so let's just block it out. What happens here? Remember, the black was the low velocity, the red was the high velocity. Which one has higher area? Well, the black does. Okay? So as you oscillate the velocity for a non-premixed flame, the area is oscillating in phase with the velocity. The weighted area is oscillating 180 degrees out of phase. So totally different from premixed flames. There's a 180-degree phase difference. And as I had mentioned, for a premixed flame, the mass burning rate per unit distance is a constant. So again, big difference. So this just makes the point that I just said, is that for low frequencies, as you oscillate the velocity, the area is oscillating in phase with the velocity. And so for a premixed flame, the heat release is oscillating in phase with the velocity. For a non-premixed flame, what we care about is the weighted area. The weighted area goes 180 degrees out of phase with the velocity. Okay, so that's what's happening to the area for a non-premixed flame. Now let's look at the mass burning rate. Okay, so that's this, what I call this mass burning rate transfer function, and it's the oscillations in mass burning rate per area. The mass burning rate in a non-premixed flame is oscillating because spatial gradients are oscillating in time. When you have spatial gradients oscillating, diffusion rates are oscillating. And the rate at which stuff is diffusing into that Z-Stokes surface is oscillating. So and this equation just quantifies this. The fluctuations in mass burning rate are directly proportional to the gradients in the mixture fraction. Whereas for a premixed flame, mass burning rate oscillations occur through either the sensitivity of the flame speed to fuel air ratio, if the fuel air ratio is being excited, or the sensitivity of the flame speed to stretch, which becomes important at higher frequencies. So let's take these transfer functions, and let me just drop on top. So here's the magnitude of a non-premixed transfer function as a function of Struhal number. And notice, first of all, the weighted area is down here. So for all that talk I had about weighted area, it's basically irrelevant. It's a negligible contributor. By far, the dominant contributor to mass burning rate in a non-premixed flame comes from the mass burning rate term. All right? And then if you add these two up, you get the black curve, which is the heat release. So the non-premixed flame also starts with a transfer function of 1. And by the way, it's for the same reason as for a premixed flame. It's just you get these mass flow rate oscillations of fuel into the system, and the heat release in the quasi-steady limit is directly proportional to fuel flow rate, assuming you have excess oxidizer. So this transfer function also starts out at 1, but it's dominantly driven by mass burning rate. So totally different from the premixed flame. That was driven by area. This is driven by mass burning rate. Whereas for a premixed flame, area was everything. And just in order to show you what a mass burning rate contribution looked like, I turned on the stretch sensitivity of the flame. And this would be what a typical stretch sensitivity contribution would give you to the mass burning rate. And notice how these two curves are just inverted for premixed and non-premixed flame. So just to back up a step, what I showed you is that the position dynamics, the fluctuations in flame position look very similar for a premixed and non-premixed flame. The heat release is totally different physics. Okay. One other thing I want to point out here, and this is I think my second to last slide, is you get actually a 3-zone region for non-premixed flames. For a non-premixed flame, for low Struhal numbers, the transfer function is around 1. For high Struhal numbers, it goes as 1 on ST. All right? That's right here. But you get this intermediate zone where the transfer function goes as 1 on square root of ST, which shows up because of that diffusion operator. Whereas for a premixed with weak flame stretch, it looks more like this, where you only have 2 zones, 1 and 1 on ST. Non-premixed flame, you have 3 zones. Okay, so I think I've used up my time. Now, things start to get a little bit more interesting. I looked at I've talked through in detail what's happening when you have bulk flow disturbances to the heat release. You can add a whole other degree of freedom to this when you start looking at disturbances with some spatial variation, like when you start looking at what happens when you have convecting vortices in these gain curves. You start to get, I talked about interference effects controlling what's happening locally, and then you start integrating over that spatially to give you the heat release. You get even more stuff going on. I think I'm just going to stop there. It's because it's getting warm in here. And let me just wrap up with 3 bullets here. First of all, that just to emphasize, the flame is a non-local operator. What's happening to the flame here is not just a function of what the excitation is here. It's a function. It's a space-time convolution of everything that happens upstream. The flame is non-local, and you get this wrinkle convection. And so this wrinkle convection leads to maxima and minima in your gain curves. It gives you this interference phenomenon that I talked about. It also gives you the 1 on F or the 1 on Struhal number behavior in your global heat release transfer functions. I also showed you how premixed flame wrinkles are controlled by different processes in different regions. So in a premixed flame, you can have this near field region, which is controlled by linear dynamics. You can have this mid region, which is controlled by interference effects, where you can get this modulation in the flame wrinkling. Then you get this far field region, which is controlled by kinematic restoration or basically flame area destruction processes. And then finally, if we turn our attention to the global heat release, the role of area and weighted area and mass burning rate, totally different for premixed and non-premixed flames. So you have to think about them differently when you start thinking about the heat release. And that was it. Thank you.